Hey guys, Mr. McKinney here, just going over sigma notation. Um, so sigma notation may show up on the AP exam, but it'll probably be a very small portion of it, and it's kind of connected to Riemann sums, which we'll cover in class next time, which will definitely be on the AP exam. Sigma notation is basically just using some formulas, getting used to using some formulas. So the idea behind sigma notation is that you can write an integral as a limit of a sum. So this sigma, this is the symbol sigma, means sum, like S-U-M, or add up all of these things. So we're going to count from 1 to whatever n is, and we're going to have it approach infinity. So basically we're going to be adding up infinitely many different things. And each time we're basically adding up a different rectangle. So we saw this picture in the last video, and basically the idea is if I want to calculate the area underneath this curve, I can make rectangles and that'll give me a close estimate. Now if I make these rectangles smaller and smaller and smaller in width, then they will become a more accurate representation. And if I take the limit as n goes to infinity, so we have infinitely many rectangles that are all infinitely thin, then we will be able to get exactly what the integral is. So again, basically you're just learning how to use some formulas, but we're trying to rewrite a definite integral using what is called sigma notation. So this is sigma notation. And you're basically just going to have to memorize a couple of formulas and then learn how to use them. So we have the integral going from a to b, so our lower limit and our upper limit, a and b, and we're trying to find the area underneath the curve of f of x. Now, we're going to need 3 other formulas to help us. The first one is delta x, which is the width of each rectangle. So basically, to find the width of each rectangle, you take the total distance, so that was the total distance, and then you divide by the number of rectangles. So n is the number of rectangles. And then, whoops, so let's erase this. So n is the number of rectangles. Then you're going to have x sub I, which is basically just an x value. And it's going to change as k changes. But the way to find x sub I is just take a, which is your lower limit, and then you're going to do k times this formula. So you're really just going to plug in b minus a over n for delta x. And then you're just going to plug everything into your sigma notation equation. So we're saying that we have infinitely many rectangles. So, and then for each rectangle, we're doing, whoops, the height times the base. So the delta x is the width of the base, f of a particular point. So like f of the first point, f of the second point, that's the height of the rectangle. So we're just doing base times height to find the area of each rectangle, and then we are adding them, or we are doing a sum. Sigma means sum. All right, now again, basically you're just gonna have to memorize these 3 formulas and then learn how to use them. So we're gonna do a couple of examples. So I wanna do the integral from 5 to 12 of 1 over 1 plus x dx. So I'm gonna, it's matching this formula. So f of x is 1 over 1 plus x. That's my f of x. A and b are my limits. So a is 5 and b is 12. And then I'm going to just come up with these 2 formulas and plug them into this notation. So delta x is going to be b minus a over n. N is just going to stay as n, but we're going to do 12 minus 5 divided by n, which would be 7 divided by n. So that's my delta x. And then I'm going to find out what an expression for x sub I is. So a plus k delta x. So x sub I equals a was 5 plus k. K and n are just going to stay as variables. And then delta x, I'm going to plug in what I got for delta x. So 7 over n. And a lot of times you'll see it simplified as 5 plus 7k over n. Either of these is fine. And now I just need to take my delta x and my x sub I and plug them into this formula. So this definite integral can be rewritten using sigma notation as the following. The limit as, this is not x, the limit as n approaches infinity, going from k equals 1, to n. And then f of x sub I means plug in x sub I into your equation. So 1 over 1 plus, instead of x, I'm going to plug in x plus I. X sub I. So 5 plus 7k over n. That is my x sub I. So this is my f of x sub I. And then I just need my, delta x here at the end. So my delta x value was times 7 over n. Now sometimes on a multiple choice exam you might need to simplify it, but this is our answer. So it's the limit as n approaches infinity from k equals 1 to n of our function with x sub I plugged in, which I got from my formula, times delta x, which was 7 divided by n. All right, let's do another couple of examples. All right, so same idea. We're doing the integral from 5 to 7 of x to the 8th dx. And again, we just got to memorize these formulas and then learn how to plug them in. So let's find delta x first. Delta x is going to be b minus a over n. So b minus a, 7 minus 5 divided by n, which would be 2 over n. And I would hit pause and try to do the rest of it yourself and then unpause it and see if you did it correctly. All right, so let's see how you did. So then x sub I should be a, which was 5, plus k times delta x, which was 2 over n. And again, a lot of times you're going to see that multiplied out. So I'm going to go ahead and do that. 5 plus 2k over n. All right, so now I just need to rewrite it using sigma notation. I have my delta x and I have my x sub I. So x sub I needs to get plugged into my equation. My equation on this one is f of x equals x to the 8th. So f of x sub I would be whatever x sub I is to the 8th. So it would be 5 plus 2k over n to the 8th. All right, so this is what I'm going to plug in for my equation here. So we'd say it's the limit as n approaches infinity, going from k equals 1 to n. I'm going to plug this in as my f of x sub I. So 5 plus 2k divided by n to the power of 8th, and then times delta x, which was 2 over n. And that's it. So it's just a matter of memorizing these formulas, finding a and b from your problem, finding the function rule from your problem, and then plugging in all the pieces. All right, let's do one more example. All right, and I think you guys should try to do this one on your own if you're understanding things so far. Otherwise, you can just watch me go through it. So either hit pause and try it, or here we go. So a and b are the limits. So I'm going to find delta x first. Delta x equals 5 pi over 4 minus pi over 4 divided by n. I'm going to simplify that a little bit. That would be 4 pi over 4, which is just pi divided by n. All right, and then x sub I would be a, which is pi over 4, plus k times delta x, which is pi over n. I'm going to go ahead and say that's pi over 4 plus k pi over n. And then let's figure out what f of x sub I would be. So in this problem, f of x is sine of x. So then f of x sub I would be sine of x sub I, which would be the sine of pi over 4 plus k pi over n. All right, so now I just need to plug things in to my sigma notation formula. We've got the limit as n approaches infinity, going from k equals 1 to n. F of x sub I was sine of pi over 4 plus k pi over n times, and then delta x was pi over n. All right, the last thing that you might have to do with sigma notation is go from a graph to sigma notation. So the steps that you would need to do is find f of x, so you'd have to figure out what the formula is based on the graph, find the limits of integration, so in this case we're going from 1 to 4 because that's the part that's shaded, figure out delta x and x sub I, and then set it up the same way we normally would. So the only thing that's different is you have to figure out the function and you have to figure out a and b. That's what we're talking about when we say limits of integration. And here are the formulas we're going to be using. So to find f of x, this is a quadratic. And if we think about it, we've got the point 0, 0, and we've got the point 4, 4. So it's a quadratic. We know it's y equals something. I won't use a. Let's use c times x squared. Some constant times x squared. And we know we have the point like 2, 1, and we have the point 4, 4. So I can pick either of these points. These are the obvious ones. 0, 0 doesn't help me because I can't figure out what the constant is. So let's take this point 4, 4. 4 equals c times 4 squared. 4 equals c times 16. So c, whoops, would be 1/4 if I divide both sides by 16. So my equation for f of x is 1/4 x squared. You get the same answer if you plugged in the point 2, 1. 1 equals c times 2 squared, so you'd get 1/4. So that's my function. And again, my limits in this case are 1 and 4. So essentially, this area that's shaded here is the integral from 1 to 4 of 1/4 x squared dx. And I'm trying to write it using sigma notation instead of integral notation. So same steps as before. I'm going to find delta x, x sub I, f of x sub I, and then I'm going to plug everything in. So delta x is b minus a, 4 minus 1 over n, which is 3 over n. X sub I is a plus k times delta x. So x sub I would be 1 plus 3k over n. And then in this case, my formula was 1/4 x squared. So f of x sub I would be 1/4 times 1 plus 3k over n squared. So now I'm going to write my answer using the sigma notation. I'll switch colors a little bit. So this would be the limit. Actually, I'm going to run out of room if I do it up there. Let's see, where can I write this? Here we go. Limit as n approaches infinity, going from k equals 1 to n. F of x sub I would be 1/4 times 1 plus 3k over n squared times delta x, which was 3 over n. So the same process as before. You just need to figure out your equation and you need to figure out your limits. And then you're just using the same equations as before. Sorry, I got a little bit messy on this one. One quick note, some of you guys may have looked at this picture earlier and been a little bit confused because if you start at k equals 1, then it looks like we would have actually used this as our first point. And the way the picture was drawn is it used the left side. And if you can ignore this explanation if you don't care. But basically, since we're shrinking the interval, we're making infinitely many intervals. We're shrinking them down to basically be infinitely skinny. It doesn't matter what point. You're allowed to pick any point on that interval. So that's why this picture doesn't exactly match this. Technically, you're allowed to pick any point in here that you want. You guys don't need to know that. Just some of you guys would have been confused by this picture. So ignore this last slide.